So the deduction theorem, as I mentioned, is a meta-theorem, but since it's so strong and so valuable, it's nicknamed a theorem simply because we use it all of the time to help us prove theorems within logic. So here's what the deduction theorem says. It says that if we have our assumptions gamma and we have an additional assumption A, and we know that these assumptions or hypotheses prove B, then we can conclude that gamma by itself proves the implication A implies B. So essentially what this means is that to prove an implication, it's enough to take the hypothesis of the implication as a hypothesis within our proof and simply prove B. So that makes proofs of implications simpler, simply because we have an extra hypothesis we can use. And as you've seen in class, it's always helpful to have a hypothesis because it gives you a starting point. So even if we have no hypothesis here, if gamma is empty, proving an implication means we can take A as a hypothesis, or the hypothesis of our implication, to help us prove the conclusion of the implication. And much like you pointed out in class, when we were looking at the semantics of the implication operator, we had these funny cases where if A was false, then the implication was true. And one of you in particular pointed out, how does this make any sense? Because this is going to confuse our programs, because it's unlikely, right? We use this if then else statement, right? So it's not simply that you ignore this hypothesis, right? You have some other condition to satisfy in that case. So this deduction theorem is essentially telling us that the only real case we care about is if A is true, right? If we assume A is true, we want to prove B from that. So, as I mentioned in the learning outcomes section, and as you will see in the textbook, the proof of this theorem is done by induction since it's a meta-theorem, so we need to really prove it, and it's a statement outside of our logic. It's not a well-formed formula we need to prove, but it's a process that we can go through, a tool to help us to prove well-formed formula. And so we do a proof by induction on the length of the proof of B, right? So to prove this statement, we assume this part. So we assume that we have a gamma union A proof of B, and we need to construct a gamma proof of A implies B. So since we have a proof of B, we look at the length of that proof of B, and we go by induction to help us construct a gamma proof of A implies B. So in doing that, you will notice that we need to consider what a proof of B looks like, right? So there are a number of different cases to consider. Many of them are straightforward. The one that's the most difficult is if the proof of B requires, for example, the rule of inference Leibniz. Okay, so this is the one that gives us the most difficulty, and so we actually require this lemma to help us to prove that particular case. And you will see that the rule of inference Leibniz is implied here. Essentially what this says is similar to Leibniz, right? So remember, Leibniz is the case if B is equivalent to C, for example, then taking any other well-formed formula, substituting B into it and C into it gives us equivalent formulae. So whether we substitute B or C, which are both equivalent, we get something that is equivalent. So what we have done here is add on this part of the deduction theorem that we need to prove, right? So the lemma is that if A implies B is equivalent to C, then A implies that any other formula in which we substitute B and C is equivalent. Okay, and this is also done by proof by induction. So you can have a look at that as well to give yourself more experience with proof by induction and look at different ways that we can prove things by induction. It turns out that the deduction theorem actually tells us something even more. So we have this corollary. We're using different notation here, but this is the same, means the same as this, if you remember. So if we add gamma to our hypotheses and prove B, this is equivalent to writing a gamma proof of A implies B. So notice that this direction, if this, then this, is essentially the deduction theorem. And the reverse direction says that if gamma proves A implies B, and we have A in our hypotheses of gamma, then we can construct a proof of B. But this is simply just modus ponens, right? Because if we have A and we have A implies B, then we can conclude B. So now we have this equivalence. And one of the key things, as I mentioned, about the theory of this corollary in particular, is that this says that all theorems are equivalent to absolute theorems, right? Here, we have an additional assumption proving something. So this is definitely a relative theorem, but in order to get rid of all our hypotheses, right, this direction tells us we can simply add each of the hypotheses with an implication to the other side, so we could get a finite sequence of implications, and we will get an absolute theorem, right? As we take more and more hypotheses from the hypotheses to the implication side, we will get absolute theorems. So every theorem can be written as an absolute theorem. They just look a little bit different. And the other thing that will be most important for us is that when we need to prove some kind of implication, we can simply add the hypothesis of the implication as a hypothesis within our proof, and then prove the conclusion of that implication. And this usually makes things much easier because we're adding hypotheses.